Let us see now the structure of aragonite in the space group PMCN. There are 4 calcium carbonate units in the unit cell. So, we now based on the density it has been determined there are 4 calciums, 4 carbons and 12 oxygen atoms. When the actual structure is determined, these are the cell dimensions. A is 4.96 angstroms, B is 7.97 angstroms. So, this is now the A direction, this is the B direction. Remember that there is a mirror symmetry at 1/4 along this direction, and then there is a C-glide symmetry which is associated in this direction. Please note that. So, both those are the mirror symmetry positions. So, we have A B projection, we have the C value as 5.73. So, A dot B cross C will give you the volume of the unit cell from which we can determine the density as we discussed before. So, you see that the calcium atoms sit on the 4m position corresponding to the x value of plus minus 0.25 and the value of the z is 0.75. But what is more important is that they sit at on the mirror which is at plus minus 0.25. This is the mirror which is now perpendicular to the A axis, and so this sits now along the mirror plane. So, you see that there is one at 0.25 and there is one at 0.75, and these are the calcium positions. So, the additional calcium positions will appear automatically in the space group PMCN at these 2 positions. So, we have therefore 1, 2, 3 and 4. Let us go back and check the mirror symmetry. This comes at plus minus 1/4 yz or yz, and we see plus minus 1/4 half minus y and half plus z. Notice that this is half minus y half plus z at 1/4 again. So, the positions of calcium are at 0.25, 0.75, 0.25, 0.75. This is now coming at the value minus 0.25. So, this one is plus 0.25. This is minus 2.25, minus 2.25 will be also equal to 0.75 by translation. So, for example, if you take this atom onto the minus 2.5, it is up there, you translate it by 1 unit, translate it by this unit, you will get back to the 0.25. So, therefore, we have 1, 2, 3, 4 calcium positions. The carbon positions now sit at plus minus 0.25, the same mirror. So, we know that there is a mirror perpendicular to the A direction. There is a C glide which is perpendicular to the B direction, and N glide is coming up with respect to the C direction. So, we therefore see here that the carbon atom also occupies the mirror symmetry 4 equivalent points, that is plus minus 0.25, plus 0.75 and plus 0.08. That means that the carbon atoms which are shown here appear at 0.8 and 0.58 respectively, because this half minus z or half plus z will account for the value of 0.58. So, I want you to check what you should do as a homework is to see, take these coordinates and see whether they satisfy the symmetry requirements associated with this 4m position. Then you will convince yourself that calcium, carbon are sitting in these special positions. It so happens that the oxygen atom will also sit with respect to plus minus 0.25 as is shown here in this diagram. So, therefore, these occur at 0.08 and 0.08. You see that the oxygen positions are indicated in a bigger open circle which is shown up here. So, the carbon atoms came here. It so happens the 2 carbon atoms sit on top of each other. This is at minus 0.28 and 0.58, and the carbon atoms here therefore are half added to the z value. So, they sit at 0.42 and 0.92, and these 2 values therefore, this is 0.92 is 1 minus 0.08, and this value is 1 minus 0.58. So, you see carbon atoms come up these positions. So, the carbon is one above the other along the z direction. Similarly, the carbon is one above the other in the z direction. And the values of calcium are given here, they give rise to these 4 positions. So, 4 calcium positions are taken care of, 4 carbon positions are taken care of, 4 oxygen positions are represented by 0.08 and 0.48, but the positions of X and Y are different. X and Y are different. That means that we have now a coordination around the calcium atoms located in such a way that we do have the connectivity between carbon and oxygen, and then that connectivity now defines the calcium carbonate structure. So, you therefore have 8 general positions which are occupied by the second oxygen set, and the coordinates are given here, and they are represented in this projection. Now, this is a projection diagram. Now, over the last few classes, you have realized the fact that even though we represent everything in 2 dimensions, eventually the structure is 3 dimensional. So, here is a challenge for you. It will not be given as an assignment or in an examination, but I want you to generate the 3 dimensional structure of calcium carbonate by yourself as a home assignment, maybe, to find out what is the coordination around calcium, how the coordination develops around calcium, and what are the connectivities in the structure of calcium carbonate based on the diagram which is given here. If you could work that out, then you have become experts in analyzing structures, even before you go and determine the structures using X-ray diffraction or any other techniques, neutron, electron, and so on. So, effectively what is represented here is a realistic structure. The realistic structure going into the orthorhombic system PMCN with 4 of those calcium carbonate units in the unit cell, and the way in which the atoms are distributed in the unit cell. So, the calcium carbon and 1 set of oxygens all occupy the 4m position, and the 8i position, which is the general position, is occupied by 8 oxygen atoms. So, totally we have 12 oxygen atoms, 4 and 4 calcium and carbon, and this determines the entire structure in the unit cell. So, what are the assumptions we have made here? We have made the following assumptions. We have assumed that we know the structure. We have assumed that we have done an X-ray diffraction experiments, which we will do later, and we have assumed that we know the unit cell dimensions and then the density, so that we know that there are 4 molecules in the calcium carbonate structure. So, these are the things which one has to do. So, this is of course as they say, it is better to think before you do the experiment. We are now thinking before doing the experiment, and this is in terms of where the atoms are coming and where they are sitting with respect to the known calcium carbonate structure. So, if we know the structure, yes, we can definitely think about it and determine the 3-dimensional structure, right. So, this now takes us to the possibility of looking at many structures which are already known. This is not our ambition anyway. We want to find out methodologies to determine the structures in the long run, but we will look at one more, which is the very simple structure of copper oxide. Copper oxide goes into the is another mineral called tenorite, and this is the structure of copper oxide. This tenorite structure crystallizes in this space group. I want you to find out what is this space group by looking at the equivalent points and also looking at the AB projection, which is shown here. What do you think is the system? You have, for example, lot of half indicated here, and you also see that this angle is beta. So, the structure has to be A not equal to B not equal to C, and beta is 90 degrees. What is the system? It is a monoclinic system, and in this monoclinic system we have a lot of half coming up, and therefore it has to be a C centered lattice. We see here in this diagram, if we now carefully look at this particular diagram, we get a C glide which is associated with the origin over here. So, and then we also get a twofold associated with that origin. So, there is a C glide and a twofold intersecting with respect to each other with a 2 by m symmetry. So, it is a centrosymmetric monoclinic system. Apart from that, we also have the fact that these 2 and C are intersecting at this origin. So, it has to be this space group C 2 by C. So, we have inferred that the copper oxide tenorite goes into the space group C 2 by C. C 2 by C boasts itself of 8 equivalent positions, right. So, we will list those 8 equivalent positions. Those equivalent positions are generated by plus minus xyz, plus minus xy half plus z. I think 4, so there are 2 more sets which are missing in this table. We will have to add that up. Plus minus xyz plus minus x bar y half plus z. What is missing is the addition of half 0 to these 4. So, it is not purposely missed, it is not shown here. What is shown here is with respect to 0 0 0. So, there are 4 equivalent points corresponding to 0 0 0, 4 other equivalent points corresponding to the addition of half half half. It has several special positions. Now, the several special positions can be of symmetry 1 bar or of symmetry 2. 2 possibilities again exist, just like we saw the PMCM case where we had 1 bar and the mirror symmetry in the previous case. We had the position of 1 bar available, but all the atoms decided to occupy the mirror symmetry. So, here we have 4 1 bar positions that are available, and these are the corresponding coordinates. You will have to generate the additional coordinates. Here only 2 are given, that means you have to add half of 0 to each one of these to get to the 4 equivalent points. So, we know where the equivalent points are. We have very clearly and quietly determined that the space group is C 2 by C without having any information earlier. So, this is C 2 by C, and then there are these distribution of equivalent points. Now, what we will have to see is how many units of CuO are in the unit cell. So, we have to go ahead and determine the unit cell dimensions. We will determine the ABC, and we know beta is non-90. So, we have to determine the beta value also. So, once we determine ABC beta, we have the unit cell dimensions. So, we can calculate the volume of the unit cell. We can measure the density of CuO just like we did the density of calcium carbonate in the previous example. So, we know the density. Avogadro number is known, and then of course, with copper oxide given to you, we know the molecular weight. And it turns out that if we use the formula Nm equals N rho V, we will end up with 4 copper oxide units in the unit cell. So, there are 4, we can, if you want to call it a molecule, it is not really a molecule, it is a compound. So, 4 CuO units in the unit cell. So, this means to say that the choices are again clear and very clear, because nothing is in the general position in this structure, because anything in the general position will generate 8 equivalent points. So, we already know that this is not occupied at all. So, general positions we can forget about, even though we have the option of having the general positions. This particular compound decides to sit in only special positions. Now, that means to say that this will now have the choice of 5 different possibilities. It can sit, the copper atom can sit in this position, this and that, and so also oxygen. There is only 1 copper and 1 oxygen, is a much simpler example than calcium carbonate. So, both the atoms have no choice but to sit in special positions in the unit cell. So, the atoms now therefore have to sit in special positions. So, we now go and see the structure. If we go and see the structure, we see that the copper atoms are found to lie at centers of symmetry, which is 1/4, 1/4 and 0. That means it corresponds to 1/4, 1/4, 0. So, this I have highlighted it here. The highlighted one is the place where the copper atoms decide to occupy. The oxygen atoms likewise decide to occupy the two-fold symmetry. The two-fold symmetry which also generates 4 equivalent points. So, the oxygen atoms decide to go and sit there, the copper atoms decide to sit here, and so you get this structure which is written here. 4 copper atom CuO in the unit cell, the oxygen atoms lie at 0 y 1/4, the value of y being 0.416. Remember, this is a C2 by C space group, so the origin is fixed. So, now the choice of fixing the y is not independent. You see, you have a two-fold axis alone, then the y axis is arbitrary, where we fix the y value is arbitrary. But once we have a centered system like 2 by m's point group symmetry, here the origin is fixed at 0 0 0, So, the value of y therefore is coming at 416 when you determine the structure. So, the crystal structure has been determined. A is 4.65, B is 3.41, C is 5.11 and beta is 99.5. So, this gives rise to our unit cell, and therefore, we can calculate the volume. The volume of the unit cell in turn will allow us to calculate the number of molecules in the unit cell. There are 4 CO units in the unit cell. The positions of the atoms are marked in this projection again, the projection down A and B. So, C axis is coming perpendicular. So, therefore, this angle is 90 degrees. The C angle is coming in a direction which forms the angle beta 99.5. So, you see therefore, the copper atoms sit at this and that position, because they want to occupy the 1/4 along A and 1/4 along B and 0 along Z. So, once they come there, the C2 by C operation will ensure this presence of the center of the C centering will ensure that you will get an object at half. And again that half is repeated here through the center of symmetry, which is present at this half position, half along x, half along y, and therefore, that will generate this half and this one. So, the positions of the copper atoms are fixed. The oxygen atoms on the other hand occupy the value of y equals 416. So, if the copper atom is at 0, 0, 1/4, 1/4, 1/4, that is 0.25, 0.25 and 0, and then this oxygen atom comes at 0.25, 0, y and 1/4. That means the value of z is 0.25 and the value of y is 0.4. So, we can have the coordinates of this atom at 1/4, 1/4, 0. Coordinates of this atom are at 0, 0.416 and 1/4, that is 0.25. Since we know the cell dimensions, these are the fraction coordinates which I am talking about. So, 1/4, 1/4, 0 is the position of copper, then the 0, 0.416 and 1/4 are the positions of the oxygen atom. So, we can calculate the length, bond length between copper and oxygen. I want you to do this again. Remember, we are in a monoclinic system. So, you cannot just directly measure the distance between these two and say it is the bond length. You have to calculate the bond length. The value of beta comes into the picture, and so there will be a sin beta component which will come in your calculation. So, one can calculate therefore the bond distance between them. So, the geometry of copper oxide can easily be calculated, either this geometry with respect to that, or that geometry, or that geometry. Again, remember that they are all governed by the C2 by C symmetry. So, the symmetry will now allow only these possible positions for the oxygen atom. So, in a nutshell, we have seen two structures, two independent structures, and we have seen the space groups into which they can go by based upon the symmetry diagrams and also the equivalent point diagrams. And we have determined the crystal structure particulars, particularly the crystal structure details A, B, C, alpha, beta, gamma, and from that we have inferred the possible space group. So, we know the space group, we know the positions of the atoms where the space groups allow the atom positions. So, all the allowed atom positions are identified with respect to the molecule which we want to put into that. For example, in the case of the copper oxide, we can put this into 8 equivalent points if they are all in general positions, and 4 equivalent points if they are in special positions. What we then determine is the density of the crystal. Once we determine the density of the crystal, then we will have 4 copper oxide units indicated, and the moment we have 4 copper oxides indicated, we know that there are no general position occupation in this particular structure. So, this way we can determine the structure. So, what are all the things we know to determine we need to know to determine the structure? We need to know what is the molecule, we need to know how the atoms are positioned with respect to the unit cell, we need to know whether how many special positions get occupied and how many general positions get occupied, and so on. So, suppose you have a structure like this. Let me draw it. Suppose you have a structure which is let us say C26H12 is a hypothetical structure O4N2, and let us say this structure goes into a space group P21 upon C. By ABC alpha beta gamma, we find out it goes into P21 upon C. This is fine. Now, we also know the positions of the special positions, unit cell, where the size of the unit cell we know. So, the size of the unit cell we know. So, we know the volume. We know the volume. We can also measure the density. So, we know the density. And since somebody said this is the molecular formula, then we can calculate the molecular weight. So, M is known, P21 by C. So, I can calculate the number of molecules, in other words the value of Z, or the number of molecules. What is the value of N we can calculate. So, having calculated the value of N, I would like to see whether I can determine the structure. See the complexity which is associated with the structure. So far what we saw was copper and oxygen, right, and we also found that by density calculations there are 4 molecules in the unit cell. Suppose this also by density tells us that there are 4 molecules in the unit cell. Then there are 4 general positions in P21 upon C. So, we therefore have to determine 26 positions of carbon, 16 positions of oxygen, 8 positions of nitrogen, and 12 times 4, 48 positions where hydrogens can sit. Now, is it practically possible to follow this methodology which we have discussed so far to determine the structure of this? Obviously not. So, the structure determination therefore is not so very straightforward. We have taken 2 examples where we already know the structure, and so we are talking about where they are sitting. In these cases we do not know where the atoms are going to sit. 4 general positions, 26, 12, 4 and 2 atoms have to be distributed. We do not know the structure of how these atoms are connected to each other and so on. Therefore, we have to do the structure determination, and there we use the X-ray diffraction as a technique to determine this, and we will see how we do that in the coming classes. Now, we have seen the structure of calcium carbonate and copper oxide, which are 2 simple examples, just to illustrate the reality of our the fact that the information about the space group, the information about the possibility of general and special positions is a must. Even otherwise, if we know the structure, we can fix where the atoms are. If we do not know the structure also, we have to have this information before we go and determine, make an attempt to determine the structure. And that is where the whole thing boils down to. The whole thing boils down to the fact that we need to therefore have an idea of what the space group into which the crystal system, into which the compound goes into. This is a simple example. Suppose you take a protein, there will be hundreds of atoms. Now, these hundreds of atoms, suppose the protein, let us say, is crystallizing in a space group, we will see what are all the possible space groups into which proteins can crystallize. We will see that the number of space groups will not be 230, but it will reduce. We will see it in a few minutes. But the fact remains that we should know the space group information. So, when we do the X-ray diffraction experiment, we will find the unit cell dimensions. We will also have to find out a method by means of which we can find the space group information. Remember, the space group information is built in through the symmetry, and we are able to identify what are all the symmetries that are present. Now, what the presence of symmetry does to X-ray diffraction is something which we have not studied, right. So, what the symmetry does to the X-ray diffraction is the next step, and that we will study in the coming classes. So, at this moment we now have an understanding of the nature of the space group. So, now we can list out the 230 space groups straight away. Instead of going into the individual details, we have in fact examined the triclinic system thoroughly. It can go into 1 and 1 bar, the point group symmetries, and the space groups are P1 and P1 bar. In fact, we have systematically analyzed also the monoclinic system, where the point group symmetries are 2m and 2 by m. So, using the monoclinic point group symmetry, we can construct the possible space groups. We have taken examples of P2, P21, C2, and we have taken examples of PM and CM. We have shown also CC. So, we have therefore in a monoclinic system 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 possible space groups that can go into this system. And we also showed in this case that there are no other possibilities other than these possible space groups. So 13 plus 2, so 15 point space groups have been generated. Once we come to the case of orthorhombic symmetry, we have 3 point group symmetries, 2, 2, 2, MM2 and MMM. Now here you see that there are so many possibilities because we have different lattices which can come in. You see, in the case of the monoclinic system, we had a primitive lattice and a C-centered lattice, no other possibilities. In fact, we have not shown that, but maybe you can practice in one of the TA sessions we can show that the primitive, the C-centered lattice can also be I-centered and things like that. And if there is a B-centered lattice, it will go itself into a primitive lattice. This can be shown in a TA example. So the number of space groups therefore are limited in case of the monoclinic system, because the number of lattice symmetries are lattice types are P and C only, whereas orthorhombic has all possible lattices. So it has the primitive lattice generating so many of these possible space groups. We have discussed 2, 1, 2, 1, 2 and 2, 1, 2, 1, 2, 1 in great detail. We can also have a crystal system with a space group C 2, 2, 2, 1, C-centered lattice. We can have a face-centered lattice and a body-centered lattice. And of course, I 2, 1, 2, 1, 2, 1 is also possible. If you take the point group symmetry MM2, we took some examples and we studied, in fact, I think one of these, the PCA21 is the space group we studied in detail, but you see the number of space groups to which it can belong to. So there is a plethora of possibilities with MM2 symmetry and more possibilities with MMM symmetry. MMM, remember, is 2 by M, 2 by M, 2 by M. So this is the possible number of centrosymmetric space groups in the orthorhombic symmetry. The number of centrosymmetric space group in the monoclinic symmetry is corresponding to this point group 2 by M or these, and the number that is possible in triclinic with centrosymmetry is that. So the centrosymmetric crystals therefore can generate only these many space groups, though the other space groups which are shown here do not have inversion centers. So this brings us a restriction on the way in which crystallization can occur. The crystallization can occur either to generate centrosymmetric systems or non-centrosymmetric systems. And it is of importance to note that if everything is centrosymmetric, the properties as described by that material is not very exciting. In fact, the center of symmetry is a consequence of a little more perfect arrangement than in the case of a non-centric symmetry. The very fact that we say centrosymmetric and non-centrosymmetric is in that context. So if the space groups to which it goes into are non-centrosymmetric, the possibility of anisotropic properties which might develop in different directions are many more. So the non-centrosymmetric crystals are more exciting and more important than the centrosymmetric structures, even though centrosymmetric structures are necessary to get an understanding of the isotropic nature of given materials. So if a material displays a particular property along some direction, it is generally the case with non-centrosymmetric space groups than centrosymmetric space groups. Now what we will do is we will go and finish off this table. You see, when we go to tetragonal, you get an enormous number of space groups. I want you to find out which of these are centrosymmetric. Of course, now we are experts in this area. There is a 4-fold symmetry which is of course obviously non-centrosymmetric. 4 bar is non-centrosymmetric. I wanted to find out whether 4 by M is centrosymmetric. And is 4 by M centrosymmetric? We have to see 4 bar, is it centrosymmetric or non-centrosymmetric? So these are issues which come up. In fact, 4 bar could be centrosymmetric, because 4 bar has a property where you have the 4-fold along with the repetition of the center of symmetry associated with it. It is just like 2 bar. 2 bar is equal to mirror. What is 4 bar? So these are questions which I leave unanswered, so that you will make some mental calculations about which is centrosymmetric, which is non-centrosymmetric and so on. and therefore in this case you have therefore the point group symmetries are more, and there so also the possible space groups. What is very important to notice here is that in case of the tetragonal system, because A is equal to B, the basal plane is square, and because it is square, the centering of that particular square alone is not possible, and at the same time if the base is square, then the other two perpendicular directions are independent of each other, and therefore the only possibility of having the other than a primitive lattice for the tetragonal system is the body center. So, for a tetragonal system we will not get the face centered space groups or the A or B or C face centered space groups, because of the fact that A equals B, that decides that we cannot have this, and this is the case which we should remember. On the other hand, if we go to the cubic system now, the cubic system has several point group symmetries, and cubic is unique because we have A equals B equals C, alpha, beta, gamma are 90 degrees. The only clear cut symmetry that has to be and must be present in a cubic system is the threefold symmetry, and that should be along the diagonal. If you see the threefold symmetry here, 3, 3 bar, 3, 3 and 3 bar, all these symmetries are along the 1, 1, 1 crystallographic direction. So, by 1, 1 we will soon understand and try to see how these crystallographic directions, crystallographic planes and things like that develop when we now try to understand the internal symmetry associated with the unit cells, which we have not touched upon so far. What we have done is the internal symmetry with respect to the point groups and the space group distributions, the generation of equivalent points. We have taken two realistic examples and see where the atoms are and so on. But how do we identify the position of the atom with respect to the internal structure of the unit cell is something which we will study in the near future. So, what we therefore see here is the tetragonal, the cubic, and then of course trigonal and hexagonal are given here. In case of trigonal and hexagonal, again we should have only the primitive lattice in both these cases, because you have the angle 120 degrees in that case, gamma is 120 degrees. So, we will not have any other body centered and so on. And at the same time we also have this rhombohedral symmetry. We have not discussed much of rhombohedral symmetry. Very rarely we come across rhombohedral symmetry compounds, even though they are becoming more and more interesting with the fact that some of the perovskite related conducting materials and so on have a rhombohedral structure, but that is something which probably is a little advanced for us. So, this from here on we will see how the presence or absence of center of symmetry brings in different natures in the space groups.